Hey everybody. Today we're looking at another optimization problem. I'm going to do problem 62 from section 3.7 of Stewart, 8th edition, late transcendentals, but this problem is totally typical. During the summer months, Terry makes and sells necklaces on the beach. Last summer he sold the necklaces for $10 each and his sales averaged $20 per day. But when he increased the price by $1, he found that the average sales decreased by 2. Find the demand function, assuming it's linear, and then let's do some optimization about how to set the price to get the maximum profits. When we're talking about a demand function, we're looking for a relationship between price and quantity. We'd like to know how many are sold at specific prices. This problem is essentially telling us what our variables need to be. Price, let's call it P, and number sold, quantity, let's call it Q. We also can write down specifically what we need. We need Q, the number sold, as a function of P. This is nice to write down. It lets me know specifically what I'm going to view as my X value, the independent variable, what I'm going to view as my Y value, the dependent variable. So P is going to be like my X, and Q is going to be like my Y. Now this problem tells us that there is a linear relationship between these two variables. When I think of straight lines, I immediately think of point-slope form. It's the most universally useful form for the equation of a line. In general, y minus y1 equals m times x minus x1. So m is going to be the slope, x1, y1 is going to be the point through which the line passes. Any point through which the line passes. Now, here we don't have x's and y's, we have p's and q's. Let's rewrite this. So y is going to become p, so q minus q1, equals m times, now x is going to become p minus p1. And again, this is using the assumption that they give us that the relationship between p and q is linear, that we have a straight line. Okay, the problem gives us additional information. It tells us that when the price is 10, he sells 20 necklaces. This is my P1, Q1 in this situation, and tells us a point through which this line passes. So let's plug that in. P1 is going to be 10, and Q1 will be 20. So Q minus 20 equals m times P minus 10. Fantastic. Now we just have to find the slope. They tell us that for every dollar he raises his price, he's going to sell 2 fewer necklaces. That's telling us a rate of change. We should be able to extract the slope from that. So slope, we know, is rise over run. The rise is going to be the change in the y values. The run is going to be the change in the x values. Here, the y values are q. So delta q over delta p. The x values are represented by p here. So we need the change in q over the change in p. We know, again, from reading the problem yet again, that when he increases his price by 1, he decreases his sales by 2. So this slope is going to be negative 2. For every dollar, P increases, Q decreases by 2. And therefore, I have a complete linear model for the demand function. Q minus 20 equals negative 2 times P minus 10. Let's just finish up this problem by simplifying this and writing it specifically as a function. Q equals some function of P. So I'm going to distribute this. Q minus 20 is negative 2P plus 20. And then I'll add the 20 to the other side. Q equals negative 2P plus 40. So there's our demand function. Part B of this question asks us what price will maximize the profit that Terry makes from selling his necklaces. Let's write down a profit function. Let's call it capital P it's going to be revenue, the amount that he takes in, minus costs, the amount that goes out. His revenue is going to be the amount from selling the necklaces, which is going to be the price per necklace times the number sold. So P times Q, little p times Q. His costs are going to be $6 per necklace times the number of necklaces, 6Q. This is the function we need to maximize. In Calculus 1, though, we only know how to maximize or minimize functions that have a single variable. So we need to get out P or Q and replace it with some function of the other variable. Fortunately here, we have a demand function, Q as a function of P. We can take out Q here, replace it with negative 2P plus 40. Here's what happens when we do that. We get P times negative 2P plus 40 minus 6 times negative 2P plus 40. So wherever I see Q, I replace it with negative 2P plus 40. Let's do a tiny bit of simplification here to make the calculus a little bit easier on the next step. I get negative 2P squared plus 40 as I distribute here. And then there, I get plus 12P minus 240. Combining like terms, negative 2P squared plus 52P minus 240. That is the function that we need to maximize. In order to optimize functions in Calculus 1, however, we need to know domain. We need to know what values of P actually make sense in this problem. All of our techniques for doing maxes, and absolute mins at this point rely on understanding the domain. So we need to know what values of P make sense. Well, certainly we can assume that the price is going to be positive. A negative price, even if it is possible, certainly will not help Terry maximize his profits. 0 less than or equal to P. What about a maximum price? Well, certainly Terry could, in theory, charge as much as he likes for his necklaces. However, our model here has Q as a function of P. We can't have negative quantity sold. That's just not something that makes sense. So the most that Terry can charge where our model makes sense is going to be the p-value that lets Q equal to 0. So setting Q equal to 0, I get P equals 20. That's going to be the maximum price we're able to consider. Fantastic. Now we have the function we need to optimize and the domain of consideration. We're going to use the closed interval method. We're going to find all the critical values of this function on this interval. We're going to plug those values into the profit function. We're going to plug the endpoints into the profit function. Wherever we get the largest value, that's going to be our maximum, the price that will maximize Terry's profits. Make a little bit of space here. So we need the derivative, P prime. Fortunately here, that's fairly simple. It's negative 4P plus 52. To get critical values, we say, where does this not exist? And where is it equal to 0? It's a polynomial, so it's always going to exist. We only have to think about where it's 0. 0 equals negative 4P plus 52. So I move the 4P to the other side. I divide by 4, and I get P is 13. That's a critical value for this function. You cannot assume that the critical value is an absolute maximum. For all we know at this point, it could be a minimum. Maybe he should really not produce any necklaces at all in order to maximize his profit. We need to manually check that this is in fact a maximum. We need to find the profit when he charges $13 per necklace. we need to compare it to the profit when he charges nothing and the profit when he charges 20. So we take 13, we plug it back into the original profit function. Profit was, as a function of P, equal to negative 2P squared plus 52P minus 240. When I plug 13 into this, I get $98. When I plug 0 in, I get negative 240. And when I plug in 20, I get 0. From all of this, it's clear where the maximum is. The max profit is going to be $98. And that occurs when he sets a price of $13 a piece.